Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 7, Lesson 6. And this is the review of rotational dynamics. So Unit 7 is called Rotational Dynamics. So in rotational kinematics, we learned about rotational motion. We measured how far something rotated, what the angle of rotation was, sometimes called angular displacement. We said, what was its original angular velocity? What was its final angular velocity? If its angular velocity at the beginning and the end were different, that meant it had an angular acceleration that was not zero. And of course, all of this happens in a certain amount of time. These were the rotational kinematic variables. They each came from or related to linear kinematic variables, V initial, V final, A, T, and X. And they led us to our 4 rotational kinematic equations, 2 starting with theta equals and 2 starting with omega final. And they, of course, related to our kinematic equations, our linear kinematic equations. These are our rotational kinematic equations, not dynamics. Dynamics, we'll get to in just a sec. So omega final squared is omega initial squared plus 2 alpha theta. Omega final is omega initial plus alpha t. Theta is 1/2 omega initial plus omega final t, and theta is omega naught t plus 1/2 alpha t squared. That should all be really review. A, because at the beginning we learned this stuff for linear motion, and then B, this was rotational kinematics. Rotational dynamics addresses the equation, what is the cause or the source of, or the antecedent of this angular acceleration? Why, if something's rotating, does it rotate faster, 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 or slower, slower, slower? And the reason we said was angular acceleration is caused by torque. And given a certain amount of torque, the angular acceleration is inversely proportional to an object's moment of inertia. And then we defined these 2 things. We said torque was the product of force and distance, how hard you push times how far the force is applied from the pivot point. And moment of inertia, if we're just talking about one piece of matter. I got this cute little 3D printed dog from the tech people here on campus. So if the dog is spinning around in a circle around my head, it's orbiting around my head, the dog's mass times the radius of the circle the dog goes in. Now the dog itself, has a kind of a round head and has a radius, but that radius doesn't matter. We're talking about the radius of the circle the dog goes in. And that's the moment of inertia of a piece of matter spinning in an orbit, mr squared. Now sometimes you've got something like this remote control could spin around in a circle, but I'm not going to take this whole mass and multiply by r squared. If this is the center of rotation, some of the matter is out here and some of the matter is closer, some of the matter is closer. So we could do a long detailed sum up all the mr squareds for each little molecule of matter. And as you go farther in physics, you will learn how to do that. But for now, there's just a table in your book that says for things with different shapes, what their moment of inertia is. And you can look that up. But for a simple shape like a dog that's traveling around in a circle, its whole mass times the radius of the circle it travels in squared is its moment of inertia. That is the big deal for rotational dynamics. Torque equals I alpha, or alpha equals torque over I. That is the big idea. Now, then there are a couple more advanced topics in the chapter. Angular momentum. And I know you're sad because I just wrote a regular lowercase l there. Don't worry, I'm going to change it. Angular momentum. There we go. We've got our big capital L there because angular momentum, L equals I omega. That's angular momentum. And we've got rotational kinetic energy or angular kinetic energy. That's most fun to write it like this, K-E rot. The rot stands for rotational. Now, linear momentum, P, was mv, mass times velocity. Mass is like moment of inertia. Velocity is like angular velocity. We're still translating letter for letter. X becomes theta, V becomes omega, A becomes alpha, T stays T. Regular kinetic energy was 1/2 mv squared. So rotational kinetic energy is 1/2 I omega squared. It turns out that angular momentum has a unit that is different from the unit for P, linear momentum. Therefore, angular momentum and linear momentum are conserved separately. We can't add them together. However, kinetic energy, just like all kinds of energy, has the same unit as linear kinetic energy. All energy has the unit joules, which is the same as newtons times meters, which is the same as kilograms times meters squared over seconds squared. Since all kinds of energy have the same unit, they can all be added together or subtracted. So if I'm conserving energy, I take all the energy at the beginning, rotational kinetic, linear kinetic, gravitational potential, heat, whatever there is, and set that equal to the sum of all those same kinds of energy at the end. Oh, I left out spring potential. All have the same unit. All right. So what I thought I would do for the final thing in this video, which is going to take a little bit of time, is I thought I would do an example problem. And I thought I would take the time to do this one example problem multiple different ways. So let me tell you what I have here. I have a board that is attached via a hinge to a wall. So the wall can push the board to the right, the wall can push the board up. Earth pulls the board down, the board has a mass m, so right along the center of the board, Earth pulls it down. There's a little box of mass m2 sitting on the board. Let's say that's 3/4 of the way along the board. And then there's a rope, again, attached to the wall up here that's pulling, and this angle is 40 degrees. So in a problem like this, sometimes they would tell you the length of the board, sometimes they would not. And we would probably tell you the mass of the board and the mass of the box. And so what I'm going to say is, given M1, mass of the board is, let's say, 10 kilograms, and the mass of the box, M2, is 50 kilograms. Given those things, what is our X? How hard does the wall push the board right? What is our Y? How hard does the wall push the board up? And what is T? How hard does the string have to pull on the board? So that is the question. I'm going to answer the question more than one way. And I'm going to show you that regardless of which way I answer the question, I'm going to get the same answer. I'm looking around for my calculator. Yay, I found my calculator. Yay. So we'll use that. So first, let's start with what's probably going to be the easiest way. And that has to do with where I select as my pivot point. This looks like a great place to choose as a pivot point, right here at the left end, because I'm going to eliminate 2 forces. However, do you see that if I choose this pivot point, I will also eliminate 2 forces, T, and I also eliminate our X. So it turns out that if I choose this as my pivot point, things are going to be easier. So let me start by doing that. So I'm going to choose this as the pivot point. So in just a moment, I'm going to suggest that you press pause and write down the equations and see what you get. The three equations: the sum of the horizontal forces equals 0, the sum of the vertical forces equals 0, and the sum of the torques equals 0. And do that with this being the pivot point. Don't solve the equations yet. Come back and see if you get the same equations as I do. Okay, so this is the pivot point. On your mark, get set, go. And then come back when you've got those three equations. All right, and hopefully you press pause and you wrote the equations and you're back. So let me see if I can get myself a little bit more paper here. There we go, to write those equations on. So the sum of the horizontal forces is 0. What are the horizontal forces? Well, our x pushes to the right and pushing to the left, so I'm going to make it negative, is t cosine 40 degrees. And that sum is 0. So I hope that's what you got for your horizontal forces. For your vertical forces, sigma Fy equals 0. I got pushing up Ry. I also see t sine 40 pushing up, so I'm going to make that positive. T sine 40 degrees pushing up. And then pushing down, I've got M1G and M2G, where M1 and M2 are 10 and 50. So I'm going to have minus 10 times 9.8 minus 50 times 9.8. 10, 9.8 minus 50 times 9.8 equals 0. Now, later on, that's going to become 10 plus 60 times 9.8. But I'm not going to add them together yet. I want to be really explicit that there are 1, 2, 3, 4 vertical forces. 1, 2, 3, and this component is 4. All right, so that's my second equation. This equation has two unknowns, our x and t. This equation has two unknowns, our y and t. So overall, I have 3 unknowns. I'm not yet ready to solve because I have 3 unknowns and only 2 equations. So here's my third equation, the sum of the torques, sigma tau equals 0. I'm using color here to distinguish among these different equations, just so I can write things closer together, but you can still see what's what. We said this is going to be the pivot point. So the distance this force is applied from the pivot point is 0, so no torque. This one, the line of action contains the pivot point, so that torque is 0. So all I have left is this force and this force and this force. But this is the pivot point. Our y makes it spin clockwise. So I'm going to say Ry times distance. Oh, I still don't know the length of this beam. So I'm just going to call it L, the length of the beam. Force times distance. Clockwise. So I'm calling clockwise positive here. This and this make it spin counterclockwise. So I'm going to say minus force times distance minus other force times distance equals 0. I like to give myself space to work in before I fill in the numbers. M1G is 10 times 9.8. M2G is 50 times 9.8. M1G, this is a distance L over 2 from the pivot point. And I think we said this was 3/4 of the way. So this is a distance 1/4 of L here, L over 4. And some of you are worrying, oh my goodness gracious, you gave me another equation, but now you've introduced another variable, L. I understand that fear, except that since there's an L in every term, I can divide this side by L, and the L's go away. And when I divide 0 by L, the right side is still 0. So now I have 1, 2, 3 equations, and my variables are xt, are yt, are y, oh, and there's no or rx or t. So now it's time to solve the equations. So let me tell you real fast how to do it. This equation has one variable, solve for ry. Then when you stick that in here, you can find T. And when you stick that in here, you can find Rx. And I'm going to take just a moment to show you what that would look like on my calculator. All right, I'm going to solve for Ry. So I'm going to take these two and put them on the right side, and they're both going to be positive. So I've got 50 times 9.8, and I'm going to divide by 4, and that gives me 122.5. And I'm going to add to that 10 times 9.8 over 2, which is 5 times 9.8. 5 times 9.8, add to that. And I got 171.5. So Ry equals 171.5. It's a force, so I'm going to say newtons. Does that make sense? So let's see if that is making, I'm just going to intuitively, 9.8 over 4 is about 2.5. 50 times 2.5 is about 125. And 5 times 10 is about 50, and 125 and 50 is about 175. So intuitively, that works for me. 171.5. All right, now that's Ry. So I can take that and subtract 10 times 9.8, and then subtract 50 times 9.8. In other words, I'm going to subtract 60 times 9.8. And that gives me a negative number, but when I move it to the right, it becomes positive. And then I'm going to divide by sine 40. And I got 647.95. I'll call that 648 for T. T equals 648 newtons. And then, now that I know T is 648 newtons, I just have to multiply by cosine 40. And I got 496.3. I'll call that 496 for Rx. 496 newtons. Ta-da! So that was this problem solved one way. Now let's take the same problem and use the left end as the pivot point. So you see how I've done that. Now I'm going to use the left end as the pivot point. So I'm going to write my equations over here, just to be fun and make it look different. And I'm expecting to get these same answers. Right, these ones right here. So let's hope I get these answers again. Fingers crossed. Okay, so with the left side as the pivot point, well, actually with the left side as the pivot point, that doesn't change my fx and my fy equations, does it? So we're just going to write those again. Sigma fx equals 0, rx minus t cosine 40 equals 0, and sigma fy equals 0, and that was ry plus t sine 40 minus 10 times 9.8 minus 50 times 9.8 equals 0. And now it is this third equation that's different, right? So feel free to press pause if you want to do this on your own, or since you already did the first one on your own, feel free to just follow along. But we're going to do sigma tau, or the sum of all the torques, equals 0. About this point, we've the distance from the pivot point to where these forces act is 0. So I'm going to do this force times the distance, this force times the distance, m1 g is 10. 10 times 9.8 times distance, L over 2, plus 50 times 9.8 times the distance, 3L over 4. This is 3/4 of L. These two make it spin clockwise, and so I made those one sign. This makes it spin counterclockwise, so I'm going to say minus force times distance equals 0. The distance is the whole length L. For the force, I'm going to break T into components. I've got my T perpendicular, which I'm going to keep, and I've got my t parallel, which I'm going to throw away. So t perpendicular is t sine 40. Do you see that if I were to draw a triangle here going right, I'm sorry, left and up, I can do physics, but left and right is hard. Left and up. So this left side is adjacent to the 40-degree angle, and this upside is opposite. And since sine is opposite over hypotenuse, that's why this is sine 40. Again, these L's go away. And again, this equation has one and only one variable. Now, before this equation down here, the one variable was Ry. Now the one variable is t. So I'm going to solve for t. How am I going to do that? I'm going to take t sine 40 and put it on the right. And then all this is just numbers. So I'm going to find what those numbers are and divide by sine 40. Let's do it. Can you see my calculator? There we go. So 10 times 9.8 over 2 is 5 times 9.8. And then 50 times 9.8, 50 times 9.8 times 3 divided by 4. And then I'm going to add those two numbers. And then I'm going to divide by sine 40. And hopefully I did that right. But I got t is 647.9. Okay, so that's t is 647.95. I'm going to call that 648. 648 newtons. Do you remember what we got for t before? Oh, 648 newtons. Yay, it worked. All right. And then I'm going to plug into these two equations, which we had before. It should work, but let's just do it real fast. 648 newtons. So if t is 648, I'm going to multiply that by sine 40. And then I'm going to subtract 98. And I'm going to subtract 50 times 9.8. And it gave me a negative number, but when I put it on the right, it becomes positive and tells me what Ry is. So Ry is 171.5. Yay. Which is what we got over here for Ry. And then Rx is just t, this 648, times cos 40. 648 times cos 40, 496. Hey, look at that. Rx 496 before, and we just got Rx equals 496 newtons. So it did not matter if we used the left end as the pivot point or the right end as the pivot point. Either way, we got exactly the same answer. In fact, you could have used the center as the pivot point. You could have used here as the pivot point. You could have used 3% of the way along the rod as the pivot point. And all of those different ways, you would get exactly the same answer. Now, the final thing I'm going to show you is maybe a little bit harder. I want to show you solving the same problem using that idea of line of action and lever arm. So let's go back to using this left side as my pivot point. The only line of action that is really going to be a challenge is this one here that contains this diagonal force. So remember, for the torque equation, and I'm going to write on this paper now since it's the last time we're using it, sigma torque equals 0. For the torques, I've got the M1G, if this is my pivot point, M1G and M2G making it spin clockwise, this making it spin counterclockwise. So M1, 10, G, 9.8 times distance, L over 2, plus M2G, 50 times 9.8, there's M2G, times the distance, 3L over 4, minus, now for this torque, instead of breaking T into components, I'm going to use all of T, and I'm going to break this distance into components. Instead of L, I'm going to use this lever arm. I'm going to go from the pivot point, not to the place where the force is applied, but to the line of action. And I'm going to take the shortest distance to the line of action, which is the perpendicular distance. And this right here is my lever arm, L-E-V-E-R-A-R-M. And so that's what I'm going to put in here, the lever arm. Do you see that if this is L and it's the hypotenuse, this is 40. So this side is adjacent to 40 and this side is opposite 40. And therefore this side is L sine 40. That wasn't so hard. Now, rather than solve this equation, I'm going to cross off the L's and I'm going to ask you to compare it to this equation that we used right here. Do you remember this equation when we used this as our pivot point? Let's compare the purple and the black equations. Oops, there was an L over 2 there. I erased when I folded my paper. Let's fold my paper at a more appropriate location. There we go. So let's compare these two equations. 10, 9.8 crossed out L over 2. 10, 9.8 crossed out L over 2. 50, 9.8, 3 crossed out L over 4. 50, 9.8, 3 crossed out L over 4 minus, now the previous equation said T sine 40 times crossed out L. And this says T times crossed out L times sine 40. Is T sine 40 L and TL sine 40, are they the same thing? Yes, they are. So it doesn't matter if I break T into components or if I break this distance into components. And that's what I'm really doing when I use the line of action, the line of action. Remember, line of action means line of force. It's the line that contains the force. And the lever arm is the shortest distance from the pivot point to the line of action. For something like this, when the force is applied already perpendicular to the line joining the pivot point to the place where the force is applied. See this line of action, the shortest distance from the pivot point to that line of action is right here, the distance we used. So we didn't have to worry about that for these perpendicular forces, but for the diagonal forces, we could worry about it and we get the same answer. So I've shown you one problem, solved 3 different ways, and we got exactly the same answers all 3 times. Super exciting. All right, well, that is the Unit 7 review. I hope you've enjoyed, and I hope you're having a great day. I'll see you soon in class. Bye-bye.